All right. So, today's talk, I'm gonna start with talking about operations research, what it is, and yeah. Sorry. Yeah, I said I would forget it, and then I forget it. Yeah, is okay now? Okay, great. Okay. No, yeah, I was saying, so today's talk, it's about operations research in an uncertain world. And the way I'll proceed here is I'll start with talking about operations research, what it is, and give a little bit of historical context and its historical evolution. Then I'll talk about what I mean by uncertain, and then talk about qualitative methods for taking uncertainty into account within optimization or operations research approaches. And then we'll conclude with some like practical guidelines and the practical example from our team. Okay, so to begin with operations research. So operations research and optimization, they're keywords that are very connected between them. But optimization is rather well known by a lot of people, whereas operations research is sometimes not so well known. So I wanted to start with just putting the field of operations research in context with respect to other scientific disciplines. So for me, it's at the intersection of applied mathematics, algorithmics, and decision science, because we really look at the ways of expressing things mathematically. So we work with a lot of mathematical models, but we also try to solve these mathematical models using algorithmic tools. And then we analyze also the effects of decisions on policymaking, or we sometimes are concerned with also like the risk behavior of decision makers, etc. So in that sense, there's also an intersection with decision science as well. So in particular, operations research is a subfield of optimization, because when you think about optimization, a lot of people do it. For instance, in machine learning as well, they do a lot of optimization. But here we're talking about a specific discipline of optimization where we are more concerned with economic problems and mostly decision-making problems that are faced by decision makers, that they be managers, politicians, or engineers. Okay, so these problems, they're typically expressed in terms of decisions, costs, and constraints. So mathematically, if you look at the formulation here, it will basically be this expression where you have the minimization of a function, which represents cost, using the vector x here, which represents decisions. And then these decisions should be contained within a set that represents the constraints of the problem. Okay, so that's the most compact way of expressing such a problem mathematically. So once we have this expression, then we use tools coming from different disciplines, such as algorithmics, economics, mathematics, and so on, to solve these problems. And the end result will be a decision-making tool in order to guide people who make these decisions in doing so. So some of the well-known examples of operations research problems, I think you will know this one. For instance, route optimization. If you ever use Google Maps and you ask the question of, okay, what is the best way of going from point A to point B? What will happen in the background of Google Maps is a mathematical representation of that problem, and then some algorithms applied to this problem to provide you with the solutions that are proposed in Google Maps. So that's a very well-known problem. There are also vehicle routing problems that are very well-known. Some planning and scheduling problems, network design problems, supply chain management problems. As Louise mentioned, they have been quite quite the discussion last year after COVID with some supply chain disruptions. So that was a focal point in the news and everything. So all of these problems fall under the umbrella of operations research. So here I want to take up an example with you to give you a more concrete idea of how it's done and what it corresponds. So we'll take up a nurse scheduling problem. So basically here the idea is we have the nursing staff of a hospital, and then we have different services of the hospital and their demands over, let's say, a week of how many nurses they need. And then the idea would be to decide which nurses come when they are on call, and to which services they're assigned to. And then these decisions should try to maximize the satisfaction of demands of different services while also respecting practical constraints, such as if people have days off, then they shouldn't be working during their days off, and also legal obligations or sometimes contractual obligations, things like if you are on call a certain night, then the next day you shouldn't be working, so on and so forth. And all of these will come together and we'll apply some algorithms. And then the end tool will be just a timetable for all of the nursing staff of the hospital, and with their corresponding services and with their working days. And the nice thing here is that this is a but this is a tool for helping decision making. So the hospital manager could interact with this tool, maybe change some constraints, maybe add some constraints, maybe change some criteria in the optimization, and interact with this tool to obtain different alternative solutions, and then choose among these solutions the one that would be more convenient. And in that sense, operational research tools maybe differ from, let's say, tools based on machine learning, where sometimes it's not very obvious how you could interact with this tool and obtain different solutions corresponding to different criteria. Okay, so next I would like to give you a different panel of applications. So these are all examples that are coming from our research team here at INRIA Bordeaux. So we have, for instance, a kidney exchange problem, so planning of kidney exchanges, maintenance planning. So this is a problem that we have worked on with the French electricity production company, EDF. Network design problems, planning of phytosanitary treatment. So this is an agricultural application, maritime transportation problem, and then the planning of energy mix for future production. So this is as well an industrial collaboration that we had with the French electricity distribution company, RTE. And you will see that so all of these problems, they actually come from very different industries. So you have healthcare, you have energy production, you have sometimes retailing, agriculture. And the important thing to note here is that we are not experts in each of these fields, obviously, but we are able to talk to industrial people or decision makers and then understand their problem and express this problem mathematically within a mathematical formalism with which we can work. So our mathematical paradigm or formalism of choice is called mixed integer programming. So this basically consists of optimizing a linear function under linear constraints using decisions that can be either continuous or integer. So this is a very famous class of problems, and actually all of the applications that I cited previously, we can cast them within this formalism. And what's nice about this formalism is that then there are some standard algorithms that we can apply. So this can either be coming from existing implementations like commercial solvers such as Cplex or Gurobi, maybe that you have heard of. Or we can also develop dedicated algorithms that will often use a combination of different algorithmic tools such as enumeration and some decomposition algorithms that will aim to exploit the structure of the problem and try to solve the problem as a combination of the solution of smaller problems, so on and so forth. So the combination of all of these tools and the research within this field and on this paradigm, on the paradigm of mixed integer programming, have made it so that over the years we are able to solve many theoretically difficult problems. So I would like to talk about that a little bit. So basically, yeah, what to know here is that most of the problems that we consider in operations research are theoretically very difficult problems. So basically what I mean by that is practically, if you take these problems, the solution time will typically increase exponentially as a function of the size of the instance. Okay, so as the instance sizes grow, then we don't have a lot of hope to be able to solve these problems in a reasonable solution time. At least theoretically, that's the understanding. But thanks to the tools that I have mentioned previously, we have actually made quite a bit of progress over the years. And maybe the best illustration of this progress is through the traveling salesman problem. So this is a very famous problem that has been studied in mathematics and in informatics as well. It's very easy to express, but it's very difficult to solve. So basically, the idea is you have a traveling salesperson that needs to visit a set of n cities, and you want to find the shortest cycle that goes through each of these cities exactly once. So here on the right, you have an example of such an instance with 10 cities in Germany, along with the optimal tour that corresponds to this. So basically, if you want to sort of have an understanding of the difficulty of this problem, you can consider enumerating all of these solutions. Keeping in mind that all of the solutions for n cities, it corresponds to n factorial. So for 10 cities, you could do this under a fraction of a second. Whereas if you take 30 cities, it will probably take you thousands of billions of years of computation, even with the current supercomputers. And even if you had thousands of them, that would still take you 35 billion years. So this is just to tell you that so this is not a way to approach this problem. And if we want to solve these kinds of problems, we should probably do something a little smarter. And that's where the research and the algorithmic development in this field comes into play. So if you look at the history of this problem, starting from the 50s, you'll see that we increased from instances of size 50 to nowadays instances of size 50,000. And this is one of the largest instances that has been solved to exact optimality to date. And it corresponds to an optimal tour of all of the pubs in the Great Britain. So you have this nice picture here. So and this progress has been made possible by the various algorithmic developments. And if we accept some suboptimal solutions, we also see that we are able to solve even larger instances to near optimality. So for instance, there's a tour of the 1.9 million cities in the world, which was solved to 0.04% of optimality. and a tour of some 1.3 billion stars from the Gaia project that was solved to 0.37% optimality. So you see that there is a very impressive progress here. And obviously, since 50s, the computational power has increased, but this kind of impressive progress in the solution of this problem, it's not due to that. It's mostly due to problem-dedicated theoretical results, and also the generic results that have improved and that have been implemented in software and numerical implementations. So if this problem interests you, I would suggest reading also the book of William Cook, which is one of the lead researchers on this problem. It seems to me that the book is in English, but it's a really interesting book, and it's not very mathematical, so it's easily accessible, but I think by a lot of people, so it can be an interesting read. Okay, so that we have seen here with the traveling salesman problem, it might make you know how to solve every problem in operations research. Okay, we managed everything, but that's not the reality. So actually, in reality, the problems that we face in industry, they are not as pure as academic problems such as the traveling salesman. They have much more richer structures. They are more complex, and they often will have problems such as the traveling salesman problem as substructures. So there's still ongoing research, and there's still need for algorithmic and numerical development to solve realistic, like industrial-sized problems. And maybe the RODEF challenge could attest to this. So RODEF is the French Operations Research Society, and they organize a challenge every 2 years where a company will propose a difficult problem to the research community, and then there will be a prize at the end to the research group that solved the problem in the best way. And you see that there are a lot of great companies that are involved in this, and there are a lot of different problems that have been proposed, some planning problems, some cutting problems, loading problems, scheduling problems. So there are a lot of interesting open problems in the industrial sense. So there's some ongoing research in this sense. There's also now research that is extending towards increasing the realisticity and the complexity of the problems that we encounter. This is also motivated by the different challenges that we see today in our society. So we see a lot of increase in the renewable energy production, or we see a concern around disaster preparedness because of the meteorological events, or we see also the increase in circular economy, where we have more and more repurposed materials and how they're integrated into production systems and so on. And so we need to respond to these challenges. And when we think about these challenges, we'll also see that one of the common characteristics of these problems, or the decision-making problems around these challenges, is the presence of uncertainty. So when I talk about uncertainty, it can come from different sources, and it can have different natures. So it can just be because of the system, because you're working with weather and then it's unpredictable, it's kind of stochastic or random in nature. But it can also be the context of your decision-making problem. For instance, when you think about investment problems, these are usually long-term problems where you need to decide today for the 10, 15 years of usage of a certain resource. And so you need to sort of scale your system with respect to the future demand that you cannot predict easily. Or sometimes you have medical applications where you have imaging, but the imaging is not exactly precise. So you have some measurement errors that you need to take into account. You can also not have historical information. For instance, in disaster preparedness, we don't have a lot of historical data, as well as presence of participants that are adversarial. So this means that their actions are not necessarily random or stochastic, but they're not known to the decision maker, and they can be adverse to the decision maker, which need to be taken into account. So there are different sources and different natures of uncertainty that we need to consider and maybe take into account within optimization models and operations research approaches. So how do we do that? And what happens when we try to do that? So the first thing that we'll try to do is to understand what kind of questions that this poses. So we'll take the shortest path problem. So this is basically the problem of knowing what is the best way, to go from point A to point B. And here at first, we'll assume that all of the durations of the different segments are known with certainty. So if that's the case, we can just enumerate the different paths we can take. So this guy, this guy, this guy, and this guy, and then calculate their duration, and then choose the best one, which in this case will be the third path. So that's the classical, typical scenario, which is encountered in Google Maps, basically. So now let's assume that these durations are not known with certainty. So there's some uncertainty in play. But let's assume that we have some kind of representation of this uncertainty. So basically, we have identified 3 scenarios, each with a probability of occurrence. And according to these scenarios, the segments will take different durations to pass through. Okay. So here, given this problem, like the question that we have in front of us would be to choose a path so that this path would be a good solution under this distributional information. Okay. So here I'm putting good in quotation marks because this notion of a good solution is to be determined in this problem. And here's why. Let's take the 4 paths that we had initially. So we can calculate the duration of each path under each scenario, right? So I know that if scenario 1 is realized, then these are the durations, and path 3 would be the best solution. Whereas if scenario 3 was to be realized, well, these would be the durations, and in that case, path 2 would be the best choice. So which one should I choose? Well, it depends on the scenario, right? So I should probably find a way to aggregate these different informations coming from the scenarios, potentially using the probabilities as well in order to guide my decision. So here I'm going to talk about 2 different ways of doing that. So the first way would be to use the expected value. So basically just calculating a weighted average where the weights are given by the probabilities of different scenarios. So these are indicated under the column ESP. And these would be the expected durations of each path in that case. Another approach would be just to look at the maximum realization. This is the worst case duration of each pass. So here we would have 35, 45, 50, and 38 in this column. Okay, so if you look at this information, your choice of an optimal path will depend on whether or not you're a risk taker. Okay. So if, for instance, you have a meeting and you absolutely don't want to be late for this meeting, maybe you'll tend to choose the path that is best under the worst case. Or maybe you take this path to work every day, so you do this task repeatedly, and you really don't care if from time to time you are late. Okay, so in that case, you may prefer the expected value solution here, which takes less time from the worst case solution, right? On average, but from time to time, it will take much longer and you'll be late. But maybe that doesn't bother you and you can live with the solution. So we see that there's this notion of risk and the preference of risk of the decision maker that will change kind of what the optimal solution would be and what the mathematical model behind this would be. So these are formalized in different mathematical paradigms. The first is stochastic optimization, where we assume that we know the distributional information around uncertain data, and we would like to find a decision that would work best in sort of like an average case. Okay, it would work best in average, and it would be appropriate in contexts where the risk level is low and the consequences of observations are consequences of decisions are observed repeatedly. Okay. Whereas in robust optimization, we assume that the distributions are not known. We rather represent the uncertainty by belonging to a set. We usually call this an uncertainty set. And then we would try to find the solution X, which behaves the best with respect to the worst case realization within the set. So this is more appropriate for contexts where the risk level is high and the consequences of decisions are observed either once or maybe rarely. Okay. So you have different choices and you have also different paradigms between these two. These are not the only ones. But just to say that depending on the risk preferences, you have different ways of approaching the problem that also theoretically change the kind of algorithms that can be used. Okay, so that's kind of the first characteristic of optimization under uncertainty that was not present in classical optimization models that assume the data to be deterministic. Now, the second characteristic will be the timing of decisions. So in everything that I told you just now concerning optimization under uncertainty, we had assumed that we had a decision and then we observed the realization of an uncertain parameter. But it is also possible to delay certain decisions until after the observation of uncertainty. And in that case, those decisions would adjust or adapt to the realization of uncertainty. And then we have this kind of dynamic decision-making process where you have different stages of decision, observation, decision, and potentially observation, decision again that can be repeated. And it turns out that this is kind of essential to the nature of these models and their difficulty and the solution methods that can be employed to solve them. So I would like to illustrate this with an example. So here we'll take up a disaster preparedness example. So imagine that we need to locate some healthcare centers and assign the potentially affected populations to those healthcare centers in anticipation of a natural disaster. So this natural disaster, it can be like an earthquake that we modeled with a set of scenarios, let's say, with their epicenter and the magnitude of the earthquake given in these scenarios. So a first variant of this model would consider making all of the decisions before the realization of uncertainty. So before the realization of the disaster, in anticipation of the disaster. So we would try to locate the healthcare centers and allocate populations to these centers in order to try to reduce the number of untreated patients as much as possible when the uncertainty arrives. Okay. So this is the first variant of a model. Now let's consider a second variant where we say, okay, in fact, the only decisions that we'll make before the realization of uncertainty is the location decisions. And then once we know the realization of uncertainty, so when the disaster strikes, we will do two sets of actions. First, we will locate some emergency centers. So this can also be triage centers. And then we will also assign the affected populations to these centers. Okay, so either to the hospital centers or the emergency centers. And you'll see that here, according to what happened in the realization of the disaster, I will have a different response to it. I will locate the emergency centers and the assignment decisions differently according to what happened with the realization of the uncertainty. Okay, so in this model, the blue decisions will adapt to the realization of uncertainty, whereas the red decisions will anticipate the realization of uncertainty, as well as my optimal response to the realization of uncertainty. So with respect to the first model that I proposed, that took all the decisions at this level before the realization, this model here will have less conservative decisions and it will be more realistic, right? Because it will somehow take into account this optimal response to what will happen in the disaster. So in that sense, we see that there is a difference between considering certain decisions before and after the realization of uncertainty. And this kind of difference is not something that exists in deterministic models. And it turns out that this practical difference also translates to a theoretical difference, notably in the difficulty of solution of the resulting models. And what happens is that when you have multiple decision stages that happen in this way, typically your problem, it becomes more difficult to solve. So you have a more realistic representation of the situation, but algorithmically it will become much more difficult to solve. So this is an active area of research, which is quite interesting, but also a particularity of this kind of optimization under uncertainty operations research under uncertainty framework as well. Okay, so as I'm approaching towards the end of the talk, I wanted to sort of recapitulate a little bit the notions and then give you sort of like a practical guideline of how an optimization under uncertainty project takes place. And what the sort of important practical and scientific questions that we should ask are. So starting with the data, data is, as you can imagine, is really important. How you use it, whether it's available, whether you try to deduce probability distributions from it or uncertainty sets from it, whether it's statistically significant. All of these questions, they should be considered, and the data should be used in the best way possible. And then you also have the question of risk preference. Okay, so how risky is the context in which we are taking the decisions? How frequent are the consequences will be observed? How robust do we want the solutions to be? Are we okay if we are not able to satisfy the demand from time to time? Are lives at risk? So according to these answers, you'll have a sort of risk notion, and then based on that risk notion and based on what kind of data is available and whether or not you are able to extract probability distributions, you will choose a modeling paradigm that's in accordance with these criteria. And then once you have your modeling paradigm, then the solution, of course, it depends on whether or not you already have algorithms that are available to solve the problem, or whether you need to develop some algorithms. And then it can also depend on whether you need the solutions to be explainable or not. So here, once again, operations research methods or like mathematical approaches and learning-based approaches will differ. And then the choice, it really depends on what kind of characteristics you want in your solutions. Do you want a certificate of optimality? Do you want explainability or not? And then according to those answers, you also need maybe to develop some new algorithms. And finally, once you have a solution, there's also a question of how you should test the solution. So typically here, what we need to be careful about is the data that's used to build a model that gives the solution, and then the data that is used to test the solution. And these data should be separate. We shouldn't use the same data. And then how you test the solution, it usually depends on the application. Sometimes you have access to simulations, and then sometimes you'll have some smaller mathematical models that correspond to it. And sometimes, if you're lucky, you'll be able to implement your solution and maybe get a feedback from the system. But when you have uncertainty present, this question of testing the quality of a solution as well, it comes into play, and it's an interesting question. So all of these questions, they're both practical and scientific. So you have active research areas that are working on different aspects of these points that I mentioned. So finally, I would like to conclude with a practical example from our team. So this was the PhD thesis of Rodolphe Griset, who worked at the team a couple of years ago and who is now with the French electricity production company EDF. And this actually was a thesis that's in collaboration between INRIA and this company EDF. And this problem is concerning the planning of maintenance outages of nuclear units. And it was actually proposed as a RODEF challenge as well. I think it was around maybe 2015 that it was proposed. And then after the team started working on it. So the critical thing to know about this problem is that even in its deterministic version, it's a large-scale problem with a lot of different units and with a long planning horizon. And it has a lot of constraints that are particular to the application, that are operational constraints. So already in its deterministic version, it has a very rich structure. And then on top of that, we wanted to consider the presence of uncertainty, because the maintenance outages, they have long-term implications on the electricity production. And then obviously the electricity production, also the nuclear electricity production being very critical in France, they want to make sure that when they stop production at a certain nuclear unit, that they can guarantee the continuity of the production by other units, and then they can satisfy the future demand. And so when you start talking about future demand, basically you have uncertainty, and then you need to take it into consideration. There's also some uncertainty concerning the market prices and the availability of other nuclear units that needs to be taken into account. So basically, Rodolphe, during his PhD, he worked on modeling this problem as a stochastic problem, and then devising solution algorithms to attack this problem. And what they developed was very much reliant on exploiting the problem structure and sort of decomposing the problem into smaller problems that can be solved more efficiently. And the results of this analysis, the mathematical model that he was able to develop and solve, was savings of around 50 million euros over 3 years, according to the simulations that were done based on the study. So you see that this has a quite important impact economically for this company. So it's quite interesting to see this theory in work in practice as well. So I think with that, I'm going to maybe put my conclusions up and then welcome any of your questions. I want to thank you all for your attention. And if you have any questions, please don't hesitate.
Thank you very much. Very interesting.
Sure. Yeah. Luis, I think you're muted. I wasn't sure if it was because the interpretation or. Oh, okay. Okay, so in which order should I take them? Okay, when calculating shortest path and implementing probability, if we are using a programming language, is there a standard way of representing this data like adjacency matrix? Okay. So I'm seeing, yeah, when calculating the shortest path and implementing probability, if you are using a programming language, is there a standard way of representing this data, like adjacency matrix? So the actually the version of the shortest path problem that I showed you with the probabilities, it's not much more different than the deterministic version of this problem, because you'll see that the expected values, they can be calculated quite easily. So actually you can calculate the expected value of each of the arcs individually and then solve a deterministic version of the shortest path problem in that case. So it doesn't necessarily require like a specific implementation in that sense. It's quite standard to with respect to what you would do for the shortest path problem in general. I don't know, so I'm not able to interact with the audience. I don't know if the person who asked this question, I don't know if the answer that I gave is okay or not.
Yes, actually,
Yes.
it seems that we had some technical issue because for example, I was disconnected from the call and I also don't see the questions. So if Raul can help me here, I know that we have 3 questions. So where can I read the questions? Because okay, Raul is sending me text message. This question we already answered, Raul. The one from Fabian.
Yeah, the shortest path. Yeah.
Okay.
Okay, and then I think there's a question about the application of machine learning in operations research. If I'm taking questions in
Yes,
order
yes,
that I see
actually.
them in the chat.
Hmm.
So maybe I'm gonna read the question first. So I'd like to know your view regarding the application of machine learning in operations research. Are there specific industries or use cases where ML and in particular reinforcement learning has shown particularly promising results in optimizing logistics and operations? What are some of the key challenges? How do you see the applications of ML with or evolving in the coming years? Okay, so that's a very good question. And I know I talked a little bit about learning-based methods during my presentation, just to sort of emphasize the differences between the mathematical programming-based approaches and learning-based approaches. So obviously, in recent years, we see a lot of machine learning within operations research, where people try to learn how to branch within the scheme of branch and bound, or they try to learn solutions from the structure of the problem. So from our point of view, since we are a research team that's working on exact solution algorithms, these are all in the vein of heuristics, and like before there were genetic heuristics based on evolutionary algorithms and things like that. I think the learning-based heuristics, they are sort of in that vein. There definitely is welcome addition, I think, in terms of finding good solutions fast. Um, but in terms of exact solution, I don't think we have seen a lot of contribution yet. So yeah, I think that's sort of where I am right now. I don't know if the person that posed the question would like to interact.
Mm, I
I
think,
don't
by
know
the
if
way,
people like to.
I am not. Well, no, I mean, I can interact because
Sure, go ahead.
we have. I mean, this is a very interesting topic because at at some point, reinforcement learning agents take sequential decisions based on the environment. So it is somewhat related. We have
Hmm.
a project that is somewhat related to this because we have a small autonomous sailboat that needs to solve a multi-level optimization problem. No? You need to go from point X to Y sailing, so the route is not direct. You need to
Hmm.
understand how you need to, and then you have uncertainty because the conditions might change as you move, no? And then
Hmm.
you need
Yeah,
to also you have the short-term uncertainty that maybe a big wave is coming and you need to change what you're doing. So it's very
do it.
interesting.
Yeah.
We have some other questions here. One is I don't know. Sorry, I don't know the name. I only have the questions. Also, says
Hmm.
bonjour, Aise. Thank you for the presentation. I have few questions linked to slide 10. In practice, how would you define the uncertainty set in disaster management with very few past observations? Do you need to have evaluation prior on the distribution of these extreme events? How would you take into account the fact that this distribution may change? For example, because of climate change.
Yeah. That's a very good question. So I saw that question. I don't know if people would like me to maybe come back on the slide.
Yeah, please,
I
go
don't know
ahead.
if you can see my screen. I think somewhere here. Um, so the first and foremost, so the uncertainty set and mainly the robust optimization approaches, they do not use distributional information. So we start with the hypothesis that we do not have access or we do not have enough data infer a distribution. So I think this kind of a question on probability distribution and how it would change, it doesn't affect so much robust optimization kind of models. But I think there's a very interesting question in there, which is how do you construct this uncertainty set, even if you don't use any kind of probability distribution, if you have very few historical data? And I think there you just make some assumptions on your model, and you base your model on those assumptions. But I think, yeah, the lack of data is obviously a big problem here in the disaster preparedness context. And I think there, yeah, maybe we should have some help from the statistics and data analysis side to give us these things as inputs. But when we consider these models in our studies, we usually have some assumptions over these parameters. We give some intervals, and then we usually put some constraints on the number of parameters that deviate from their sort of expected value in some sense. I don't know if that's an acceptable response.
No, I mean, I think it is. No, it's, I think that, like, it's true that if the event is sufficiently unfrequent, only based on statistics, like for example, I'm thinking of earthquakes. No,
Hmm.
I don't know. I am not a geologist, but you don't have a statistical model of how likely an earthquake is. That
Hmm.
is actually relying more on the geophysics. No, you have some indication that maybe you see small earthquakes and the probability of seeing an earthquake will increase. But in
Hmm.
any case, uh, like it is such a big change of the scenario that you just need to prepare for an, an event that is going to. It's hard to predict how the earthquake is going to impact your scenario, no? So in that sense, is is like a black swan event. I was thinking like maybe in less, how to say, in more in smoother scenarios, like when you have these predictive maintenance scenarios where you have some
Hmm.
machine, you have a probability that some of your machine breaks, no? And in this
Yeah.
case, yes, you could try to estimate and like.
Yeah.
Uh, by the way, do you? Here we have Fabian is from here INRIA. I think he was one of the guys that asked the questions.
Sure.
I don't know. I feel like I am not controlling the system. Sorry, but are you aware of
Okay.
any of these predictive maintenance scenarios combined with the logistics? Of any solution that comes to it? I don't know. It just came out to my mind. Uh,
Um, I'm not so, I don't know the exact applications, but I think you're right in some sense. So the way that you construct sort of your model and the data around it, it's very dependent on the application, right? So that's why I was trying to talk about like different paradigms as well. So for instance, if you have sufficient data that you can infer a probability distribution from your data, as you suggested, you have a machine and you can infer probabilities on the possibility of a breakdown and whatnot. You probably use that information, and in that case, you would go towards a stochastic model that uses that kind of probability information. Whereas in disaster management, you don't have a lot of historical data, so you are not able to do a lot of statistical inference. So I think in that case, it's safer to completely eliminate the probabilities and construct uncertainty sets based on some assumptions or based on some expert opinion. Maybe they are able to give you sort of scenarios that they think are possible, but you will not assign probabilities to these scenarios. You will rather try to prepare for diverse realization within those scenarios that were constructed by the experts. So yeah, that's my best answer.
Awesome. Well, no, thank you very much. Is the you? I think I will write you an email later because
Sure.
we have some unrelated. I mean, not related right now to the class problems that it would be interesting to look at from a logistics and a scheduling point of view. I don't know if we have more questions from the audience.
Thank you.
So
Yeah, please feel free to. You can even speak because I have interpretation. Normally, I should be able to understand you.
awesome. No, I mean, this is a very interesting and important topic, Aisha. And you see, uh, by the way, we have a lot of people attending, and let's see, next time, I hope we can organize this in presence. Maybe
Yeah,
we can welcome you here in Chile and, do some additional work on this. This is really interesting. Thank you very much.
sure, with pleasure, with pleasure. Yeah, thank you so much for welcoming me in this virtual environment. And um, we had some maybe technical issues, but it was really great. And thank you for the questions as well. Very interesting discussion. Yeah, I only regret that we were not able to maybe interact in a more dynamic fashion, but
Next
maybe
time,
next time we can. Yeah,
we will polish this thing. I think that today we're having some issues with Zoom. You saw I got kicked in the middle of me talking. So let's see. Thank you very much, and
sure,
hope to see you soon in another, either virtually, but hopefully in person. See you. Take care.
sure. See you.
Bye bye.
Thank
And
you, everyone,
thanks to
for being
everybody
present.
attending the Journey Scientific. Bye.
Yeah,
The the master class. See you. Bye.
bye.
Bye bye.
Au revoir, Ariel. Merci.
Recording stopped.